Professor Ing Lee for plenary speech number 2. It is my great pleasure to introduce him to you. Dr. Ing Lee received his BS degree from Seoul National University in 1990, and he got his MS and PhD degrees from Stanford University, EECS, in 1992 and 1995. And from 1995 to 2001, he was a member of technical staff at Dell Laboratories, Solution Technologies. Since September 2002, he has been with Korea University in Korea, in Seoul, Korea, and he is currently a full professor there. And he has published over 130 journal papers and 30 US patents granted and pending. His research interests include signal processing and communications and coding techniques for wireless communications. And he has served as an associate editor for ITC transactions on communication and wireless communications. Basically, he's a world-renowned scholar in this area. He was the recipient of the Best Young Engineer Award from National Academy of Engineering in Korea in 2013, and then he has been elected as an ITC fellow. Let's welcome Professor Ing Lee for his talk.
Thank you. Good morning. I'm Professor Ing Lee from Korea University School of Electrical Engineering in Seoul, Korea. It's my honor to give a plenary talk in this ITC-CSCC conference. Today I'm going to talk about new emerging area in communication techniques, which is called the wireless power communication network. For several decades, communication theorists, including myself, have been working hard to improve the performance of the communication system. And in this communication system, the major goal is how to maximize the throughput or data rates. But nowadays, a lot of progress has been made to maximize the throughput. But lately, many interesting work has been developed in regards to the wireless power transfer or wireless energy harvesting. So I'm going to talk about those wireless power transfer techniques in today's talk. So I'll give you a brief introduction of the wireless power systems, and then introduce a system model, and we will describe how to make a optimum resource allocation for such a system. And after simulation results are provided to validate the proposed system, I will provide some brief summary. So actually, the wireless power transfer has been long history. There has been two major approaches to make power transfer remotely. The first one is the inductive coupling, and the second one is magnetic resonance method. For example, inductive coupling has been applied in many devices nowadays. It has very good power transfer efficiency, but its main limitation is the distance between the device should be very short, such as short as a few centimeters. which requires almost a contact point constraint. In contrast, the magnetic resonance coupling method has a little longer distance, but its distance is still limited to maybe 100 meters, and its efficiency becomes lower compared to inductive coupling. However, even though the efficiency is rather high, major limitation of these techniques comes from the very short distance. So it may be difficult to apply to any practical mobile environments. So recently there has been a lot of research on the electromagnetic wave-based power transfer. So basically, it utilizes the regular radio frequency signal to convey the energy. The major gain and major benefit of such technique is its long range. It can be covered up to a kilometer range. So imagine a future system where once you get into a room, such as if you come into a room of this size, as soon as you enter this room, your smartphone device or laptop immediately begins to charge itself without relying on its battery. So it will be very convenient. So this kind of RF-based technology will enable us to realize such a convenient method. But currently its main limitation is its power transfer efficiency is still low, and this issue should be resolved in the circuit implementation issue. And a lot of circuit and RF designers are working hard to improve the efficiency. And today I'm going to focus on this RF signal-based wireless energy transfer. So as I mentioned here, one major benefit is that it has a much longer distance compared to conventional techniques. And it's also at the same time it allows a low cost and robust implementation. And a lot of people are talking about applying this technique to IoT or wireless sensor network and even cellular systems. However, if you consider the wireless energy transfer technique, there are many issues should be addressed before implementing in practical systems. One major difference between the wireless energy transfer system and the conventional traditional communication system is that the interpretation of interference is totally different. Because in conventional cellular systems, interference causes a lot of trouble when trying to achieve a good throughput. But on the contrary, in the wireless transfer system, wireless power system, interference can be used to improve the harvest energy. So traditional interpretation may be quite different. So we need to carefully exploit such a new property when designing energy transfer system. So I'm going to describe a little more detail in today's talk. Actually, the first studies on this wireless power transfer started maybe 5 years ago. It's a relatively quite new area in communication theory. And there has been a lot of papers still being published, but there's two major architecture. First one is called SWIFT, and the second one is called WPCN. SWIFT represents called simultaneous wireless information and power transfer, and the WPCN refers to the wireless power communication network. First is the SWIFT system. Base station communicate with the device, mobile device. But in the device, they can harvest energy based on the received RF signal from the base station. So in the SWIFT system, the mobile is able to collect energy and decode the information at the same time. So before, in the traditional communication system, the RF signal transmitted by the base station was solely used for transmitting some information. But in the wireless energy transfer system, the same RF signal is utilized to charge the battery at the mobile device at the same time. So this is called the SWIFT. And the second architecture, second popular architecture in the wireless power transfer is WPCN. And this architecture is well suited in the wireless sensor network, wireless WSN. Consider that there are lot of sensors around the node, around the field, and in most cases, a sensor nodes may not have enough battery. So one good possible scenario is first base station or separate tower beacon transmit the RF signal to charge each node, and after each node collect energy from the received signal. Then, based on the harvested energy, they transmit the data back to the AP access point. So this is a very good example of how to combine the wireless power system and the traditional communication system. So it allows a system where the tiny node do not need to have a separate battery. So in this new architecture, we need to solve several things. How to design the, for example, beamforming technology for multiple antenna need, and how to make proper resource allocation, how to assign power to optimize the throughput. And as I mentioned before, one major difference between the traditional communication system is that the role of interference. Because in the traditional communication system, every signal which is not intended to the desired source is regarded as interference. So it does no good to, it does have no gain when we try to improve the performance. But in this, for example, WPCN, any signal even from the other base station, the signal from the other base station can be utilized to harvest the energy. So that we need to take this account. So in the following, I will describe more the system. So among two major architectures, SWIFT and WPCN, I will focus on the WPCN because WPCN may be more suitable for today's IoT applications such as wireless sensor network WSN. And as I mentioned before, the hybrid access point first deliver the energy to the remotely located sensor nodes, and then each sensor node can transmit its collected data based on the harvested energy. So first in the downlink, energy is transmitted from the base station, and that process is normally called wireless energy transmission, WET. And in the subsequent phase, in the uplink, the sensor node will transmit the data back to the base station, and that is called the WIT, wireless information transmission. So we need to first jointly optimize the WET process and WIT process to maximize the overall performance. This is the conventional system, which has been proposed maybe for WPCN about 2 years ago. So the WPCN process is divided by 2 stages: wet, first downlink wet and uplink width. So for the downlink, energy is transmitted, whereas the information is transmitted in the uplink. So in a TDD fashion. So first, hybrid access point transmit the energy to the sensor node, and then in the uplink, assuming there are k different sensor nodes, they transmit back to the base station in each allocated time slot in the TDMA fashion. So first, one thing we need to optimize is how to assign the time duration for each slot, tau 0 through tau k. So the whole throughput can be written as a well-known load expression. So if you increase the tau 0, then maybe it helps to achieve more energy, but at the same time it will sacrifice the data rate. But if you have reduced the wet process, it will limit the possible energy harvested in the wet process. So it has obviously some trade-off between the downlink and uplink. So we need to jointly optimize the time. So this problem has been solved a few years ago. And one well-known problem in this scenario is that it may have a double linear problem, especially for far users. If, for example, consider a system where one user is located far away from the base station, then apparently it will receive less amount of wireless energy. But at the same time, because it is located far away, it requires a much higher transmit energy in the subsequent uplink process. So if you locate it far away, then it leads to unfair achievable rates. So it is called the double linear problem. So we need to solve this kind of issue. So conventionally, most of the wireless power techniques has been studied in the single cell scenario. But in reality, if you want to really implement in actual system, we need to consider multiple scenarios. Because if you want to implement the wireless power transfer system in this room, in this size room may have require several access